In this series, I'm going to be going over every hard problem solving and data analysis question on the SAT. This is part 1, going over every hard question related to ratios, rates, proportional relationships, and units. In this video, every question will be 3 out of 3 hard difficulty under the domain, problem solving and data analysis, and the skill, ratios, rates, proportional relationships, and units. You can see for each question up here in the top left, there will be this unique question ID. And if you look in the video description, you can see each of those question IDs along with the timestamp of the exact minute and second where I start going over the solution to that problem. And each question will have a brief description of the question topic in case you want to look through them afterwards, looking for specific types of questions. If we dive right in, we got this table. It gives us the species of tree and a growth factor for each species. It says one method of calculating the approximate age in years of a tree of a particular species is to multiply the diameter of the tree in inches by the constant called the growth factor. Right, so we're multiplying the diameter times the growth factor, and that will give you the age, or an approximation of the age. The table above gives the growth factor for 8 species of trees. If a white birch tree, so white birch is right here, the one with the growth factor 5, and a pin oak tree, so pin oak tree, that's this one, it has a growth factor of 3, each now have a diameter of 1 foot. So right now they both are 1 foot, that'd be 12 inches. In case you're not familiar with the imperial system, but that's what they already have. So I think if it's going to be talking about growth, it might not matter, but let's see. Which of the following will be the closest to the difference in inches of their diameters 10 years from now? So it basically just matters how much they grow over these 10 years. Again, like that 1 foot that they already have, the 12 inches is already there for both of them. They're both already 12. So it's just about how much they grow in that 10-year span. And just looking at it quickly, so white birch has a higher growth factor. So that looks like it's going to mean it will grow faster. And the pin oak has a smaller growth factor of 3 that will grow slower. But let me look back at how you use the growth factor, because it might actually be the opposite based on how this is, which means growth factor is kind of a misleading name, I would say, because you'd think a higher growth factor means it grows faster. But let's see. It says you find the age by multiplying the diameter by the growth factor. So that would mean this number is what you multiply the diameter by to find the age. So if this is a bigger number, that means the age is bigger, but it's still the same diameter. You see what I mean? So for instance, right now they're both 12, right? So the white birch, that means it's 5 times 12. This white birch is approximately 60 years old. And the pin oak, the growth factor is 3. So 3 times 12, that's 36. So it's approximately 36 years old. But they're the same size. So if this one took 36 years to grow to be 12 inches, and this one took 60 years to grow to be 12 inches, that means that the white birch actually grew significantly slower. Right? It's taking more years to grow to be the same size. So it's kind of an inverse relationship here. I guess it is an inverse relationship. The growth factor is not how fast it grows. It's how many years it takes to grow 1 inch. 1 inch. Right. So in that case, that means that a higher growth factor is actually associated with slower growth. In this case, again, this is kind of a misnomer, I would say. Growth factor generally would mean, right, it's a higher growth factor, it's growing faster. In this case, a higher growth factor in this problem is it's growing slower. It should be called like the age factor or something like that. That'd be a little bit weird. But and a lower growth factor means it's taking fewer years to grow the same 1 inch, so it's actually growing faster. So in this case, we're only looking at the white birch and the pin oak for this problem. But in the entire table, this one with the highest growth factor of 7.5, this is the slowest to grow in terms of diameter. And the cottonwood has 2.0 growth factor. That would be the fastest growing. It only takes 2 years to grow an inch. So just be really careful with that. They're clearly trying to trip you up with that. And I don't love that they called it a growth factor, but if they did this in a sample question, it very well could be on the SAT. So just read very closely. If they have something called like a growth factor, don't just assume you know what it is based on maybe problems you've done. Read closely. In this case, they're multiplying that growth factor by the diameter to find the age. So a higher number means it's older, it's taking longer to grow. All right, so with that in mind, what do they want? They want to say how much, or what's the difference in their diameters 10 years from now? Okay. Well, again, we don't care about the 12 inches they already have. That was a good reference to figure out like how old they are right now, and that can help you maybe figure out the problem. But we're just talking about over a period of 10 years. So if it takes 5 years to grow 1 inch, we could say that means that each year it's growing 1/5 of an inch, or 0.2 inches. Let's say 1/5 of an inch. I'll do that in red because that's what I underlined white birch in. It's 1/5 of an inch times the 10 years. And then that's for the white birch. So it's going to grow 2 inches. It's 1/5 of 10. For the pin oak, this one's not going to work out to be a whole number, but we've got, it grows 1 inch in 3 years. So each year it's growing on average 1/3 of an inch. So 1/3 times those 10 years, say that's 10/3, or that would be 3/3 is 1, so 9/3 is 3. It's 9/3 plus 1/3. 3 and 1/3, you could estimate that to 3.33. Right, it's 3.3 repeating. That's how many inches this one grows. And then we want to find the difference between these two. So the difference, they both are already 12. So it'd be 12 plus 2. This one's 14. This one would be 12 plus 3.33. We don't care about like the total because they start at the same total. It's just how much faster did this one grow? And the difference would be 1.3 repeating. And they round it closest to the difference. So they didn't say to round it to the nearest tenth, but it's just the closest one. 1.33 is closer to 1.3 than to 1.4. So that'd be C. So this was a tricky problem. It's not that hard to do once you understand what you're doing with these growth factors, but just be careful because you could think, all right, well, this one's growing 5 inches per year. So 5 times 10, it grew 50 inches. This is 3 times 10, that's 30 inches. So the difference is 20. Although then you'd see that's not an option. So hopefully that would help you figure out, oh, something else is going on here. And again, that growth factor is kind of the opposite of what you first might think it is. We have another tree problem here. A sample of oak has a density of 800, all right, maybe it's not, I mean, it's from a tree. A density of 807 kilograms per cubic meter. All right, so I know there are a lot of density problems on this new digital SAT. And density, you do want to make sure you go in knowing this. Density is going to be equal to the mass divided by the volume. Right? It's just how much, you can think of it, how much matter is packed into a certain amount of space. And by matter, like that's what gives something mass. So if it helps you to think of that as weight, because we're usually doing our calculations on a place with the same amount of gravity, so we're doing it at the surface of the Earth. So weight and mass are kind of aligned in that way here. Mass just means that, right, it's not going to change based on gravity. So like the mass stays the same on the moon, but your weight goes down because there's a smaller force of gravity. But regardless, mass divided by volume. Make sure you know that formula. You've probably used it in physics and chemistry class. You probably even used it in middle school, just like more general science classes, and maybe even elementary school you could have heard of it. But make sure you know that going in because it will just save you some time in thinking here. The density they gave us is 807 kilograms per cubic meter. So that means meter cubed. The sample is in the shape of a cube where each edge has a length of 0.9 meters. So if we draw a little cube, you don't need to draw the cube as long as you know. It would be 0.90 meters in every direction. So cube means that the length, width, and height are all the same. And so its length, width, and height are all 0.9 meters. Now, if you want to find the volume of this cube, the volume of a cube will just be the side square, or the side cubed, right? Because it's length times width times height, and they're all the same, right? So you could, or you could, if you want, you can just write it out as 0.90 times 0.90 times 0.90. So volume equals, I'm going to write parentheses 0.9 meters cubed, and 9 cubed is going to be 729. So this is going to be basically 9/10 cubed. So 729 over 10 cubed is 1,000. So it'd be 0.729, and then the meters also get cubed, so cubic meters. Right, that's your volume. So I can plug that into this equation here. We don't know what the mass is yet. And it says to the nearest whole number, what is the mass? So we're solving for the mass. I'm just gonna write a big M there. I'm doing it as a capital M just so we don't get confused with the M in meters, or the meters cubed. So divide that by 0.729 meters cubed. If you wanted, you could even just leave it like this and plug it into the equation. It would still give you that same answer because this is equivalent to 0.729 meters cubed. And now we just want to get the M alone. So I'm going to multiply both sides by this 0.729 meters cubed times 0.729 meters cubed. The meters cubed will cancel out over on the left side. Meters cubed divided by meters cubed just makes 1. So we're just left with kilograms. And now if I take my calculator, I should say on the right side, right, 0.729 divided by 0.729 cancels. Meters cubed divided by meters cubed cancels. So 0.729 times 807 gives us that M is equal to 588.303, and that would be kilograms, right? We still have the kilograms here. Let's see, they rounded to the nearest whole number, so the whole kilogram. 0.3 would round down, so it's going to be 588. That's option A. All right, so that's all you've got to do. Just make sure you do know this formula. You could figure out from the units anyway that, right, this is kilograms per meter cubed. So the meter cubed has to be in the denominator, right? You can find that from the volume, and then the mass has to be in the kilograms. But I really recommend make sure you know that, because I think it will come up, you know, a fair amount. These are the hard questions. You'll see actually a fair number of them, even just in this video, will be related to density. So make sure you've done some of those as practice. The speed of a vehicle is increasing at a rate of 7.3 meters per second squared. Okay, so it's an acceleration question. In case this scares anyone who hasn't done physics, meters per second squared, just think of it, basically it's like the meters per second that it changes per second. Sometimes they'll even say meters per second, just if you divide meters per second by seconds, then you end up with meters per second squared, right? Because it's seconds times seconds in the denominator. All right, so basically, if you drop an object, it falls at 9.81 meters per second squared. That means each second, the speed will increase by 9.81 until whatever air friction will slow that rate of acceleration. The speed of a vehicle is increasing at a rate of 7.3 meters per second squared. 7.3 meters per second squared. I'm going to write the second squared down here, just because I think this is going to be a conversion problem. And what is the rate in miles per minute squared? Okay, so you got to change meters into miles, and I always do miles as mi, even though, like, you know, on a car, especially if you're in the United States, it would be miles per hour, mph, so they're abbreviating miles to m. But in physics, I always write mi, so you don't get it confused with the m in meters. Okay, so we want to make that meters into miles, and we want to change second squared into minute squared. Now, the squared is really important there, because if you just change seconds into minutes one time, that will not, you know, be the correct answer. You need to basically do the conversion 2 times over, so that each of these seconds, like you can think of this instead of second squared as seconds times seconds. I would leave, when I'm doing it myself, I just leave it as second squared. But if this helps to explain it this first time, then that might help. So I set it up like this. You have a numerator and a denominator, right? With the units in either the numerator or denominator, wherever they're supposed to be. And now let's start with the miles, right? We want to change meters into miles. So right now, meters are in the numerator. We want that to be miles in the numerator. So I'm going to multiply by something with miles in the numerator and something with meters in the denominator, so it cancels out, right? Meters divided by meters will cancel out, because anything divided by itself is 1. So I'm going to put miles on top, meters on the bottom. Now, this is not okay to just multiply by miles over meters, because you have to multiply by something equivalent to 1, so it doesn't change the value. And by equivalent to 1, I mean, like, if you divide something by itself, it equals 1. So in this case, 1 mile is equivalent to 1,609 meters. So if you divide 1 mile by 1,609 meters, or vice versa, 1,609 meters divided by 1 mile, that's equivalent to 1, right? It's dividing by something equivalent to itself. So we aren't changing the value, right? It's going to be the same distance if you multiply it by this, or even the inverse of that, the multiplicative inverse of that. But what it will change is what units we have, because like we said, meters divided by meters will cancel out, and then we have miles in the numerator, right? So that's why you're dividing by 1609. Now, I like to set it up like this, because sometimes when you're trying to do it in your head without setting it up like this, you might multiply by 1609 instead of dividing, or divide when you're supposed to multiply. In this case, we are dividing by 1609. But if you set it up like this, then you know for sure, oh, I did it right. Okay, so we set it up like that, and we're running to the nearest tenth. Okay, so remember that at the end. But this has got us into the miles. So the miles part, we're done. Now we need to change the second squared into minute squared. And they didn't give us the unit there. Hopefully we would know that there are 60 seconds in 1 minute. Now, I wrote 1 mile up here, just, you know, hopefully it makes it a little bit more clear. You don't need that 1, because if you multiply something by 1, it doesn't change the value. But I'll do the same thing for the minutes and seconds. I don't always do that. So if you see later in the video, I don't, you know, that's fine. Just sometimes writing the 1 helps you keep track of the fact that you did, right, put that unit in there, because we start by just writing the units without the numbers. Let's see. So we want to get seconds out of the denominator. So we're going to multiply by something that has seconds in the numerator, and we want minutes in the denominator. So we'll put the minute down here, and 1 minute is equivalent to 60 seconds. So it's dividing something by itself, essentially something equivalent to itself. So this is like multiplying by 1. It won't change the value, it won't change the amount of time. It just changes the units we're representing those time in. So this will get rid of one of the seconds, right? Seconds divided by seconds. But if we want to get rid of both of those seconds and end up with per minute squared, then we need to multiply it again. So times 60 seconds over 1 minute again, and seconds like that. All right, so that means that what we're left with is 7.3. We don't need to write times 1, that won't change the value, times 60, or you could write times 60 squared or times 3600, but times 60 over, and then at 1609 times 1, and you need to write those units. And now let's write all the units as well. So minutes times minutes, that will give us minutes squared. And in the numerator, we've got miles. Okay. So now we're going to have miles over minutes squared. So miles per minute squared, the units we want. And we just can type this into our calculator. They're not looking for a fraction, luckily, so we don't have to worry about simplifying it anyway. All you have to do is type it in, get what the decimal answer is. 7.3 times 60 times 60. I guess that is simplifying it, but just easy with a calculator. So I typed in 7.3 times 60 divided by 1609. It gave me 16.33, and then it keeps going on. But so it's approximately equivalent to 16.33 miles per minute squared. Right, miles per minute squared. And they round to the nearest tenth, so that would go down to 0.3. It's 16.3. So answer B there. So I just like to set it up like this. I call this unit analysis. This is usually something you'll do in physics and in chemistry class. Just make sure that you're setting them up appropriately. The main things to keep track of are, like, should you put something in the numerator or the denominator? Usually, like, whatever you're trying to get rid of, if it's in the numerator, then you have to multiply by something that has that same unit in the denominator to get rid of it. And the unit you want should be where it's supposed to be. If you have something in the denominator you want to get rid of, you multiply it by that same unit in the numerator. And again, the thing you want in the denominator should be in the denominator where you multiplied by. And again, just make sure if you have something like seconds squared, or you might later on see something that has meters squared or miles squared, something like that, like if you're talking about area, then you have to multiply by that conversion twice. It's maybe a little bit harder to conceptually visualize it if it's time. But if we thought of, I mean, just make sure if you have seconds squared, you have to get rid of seconds squared. But say you had an area, right? If you go from like 1 foot by 1 foot and you want to make it into inches, that's not just 12 square inches. One square foot is not equal to 12 square inches. It's 12 inches by 12 inches. So that would become 144 square inches from what was originally 1 square foot. Right? Those are equivalent values because 12 inches is the same as 1 foot. But to scale it, and it's not even scaling because you're not changing the scale, you're just changing the units. To convert the units, you had to multiply by 12 squared because 12 times the length and 12 times the width. Right? So that's kind of the logic behind why you need to do this twice. Right? You can't just multiply by 60 once, you have to do it twice to get rid of those seconds squared and replace them with minutes squared. So those are the main concepts they're testing here with this unit conversion question. Here we have Jeremy deposited X dollars in his investment account on January 1st, 2001. So it's 2001, January 1st, and it was X dollars. Okay, we don't know what X is yet. The amount of money in the account doubled each year. Oh, wow, that's very impressive return. So it's doubling each year until Jeremy had $480 in his investment account on January 1st, 2005. So it's the same date. If we look at it, same day of the year. It's the beginning of the year, January 1st. But it is 4 years later. So 2005, right, 4 years passed. If we wanted, we could write out all of those years, or we could say like 2001, 2002, 2003. That's easy to do because it's only a span of, like there are only 5 years represented. It's a change of 4 years. You go in X, it ended at 480, and it's, let me separate this a little bit better. And it's doubling each time. So you could go, if you're going backwards, you're doing half. So it'd be like, all right, this is 240, 120, 60, half of 60 would be 30. Right, so what is the value of X? Should be 30, right? That would be one way to do it. If you want to do it more with like an exponential function, you could say each year it's doubling, right? So each year you're multiplying by 2. So you could say it's basically X times 2 to the power of the number of years. Because if it's 1 year past, you multiply by 2 once. If it's 2 years past, where you go to 2003, then it would be you multiply by 2 different times. So you multiply by 2 squared times 2 times 2. 3 years past, you multiply by 2 cubed, 2 times 2 times 2. So 4 years past, we'd multiply by 2 to the 4th. So X times 2 to the 4th power, that's 4 years of doubling, then that would make you arrive at your final amount, which is 480. Right? And you just go, okay, 2 to the 4th is 16. So we get X times 16 is equal to 480, or even you write a 16x. But then to get rid of that times 16, you just divide both sides by 16. And let's see, 16 divided by 16 is 1. X is equal to, well, 48 divided by 16 is 3. And then you solve this times 10. So it is also going to give you 30. So either way, you get that the answer is 30. And that's the value of X is the question. If you want to check it, just work forward. 30, and then double it 4 times 2 is 60, times 2 is 120, times 2 is 240, and the fourth time times 2 is 480. So it does check out, and 30 is what you want to enter in for your answer. All right, we have another table. It's got a bunch of states, power capacity. The table shows the distribution by location and power capacity. Power capacity is the maximum rate of power generation of the 20 largest wind projects in the United States in 2013. The total power capacity of the 9 wind projects located in Texas was 4,952 megawatts. Okay, I know this is probably going to trip some people up just because a lot of people confuse power and energy, even just some of the ways we talk about it. Power is energy per unit time. So watts is a unit of power. It's like basically how fast you're either generating or using energy. And joules would be, or if you did megajoules or something, that would be the unit of energy. But a lot of times they talk about like megawatt hours, which, it looks like that's going to be coming up here. Megawatt hours. That's multiplying the unit of power, so energy per unit time, times time. So the times will cancel out, the time in the numerator and the denominator, because per unit time times time, and it just leaves you with energy. But it sounds like a weird unit. Megawatt hours, it's megawatts times hours. Okay, so that might make this a little bit confusing for some people. Even if you haven't used those units before, you can kind of figure it out just using the units that they give you. You don't need to fully understand what's going on in the problem to always find the answer, but it does help. So if you've taken physics, that will help, or just do some of these practice problems. There are 9 wind projects located in Texas, and their power capacity, total power capacity was 4,952 megawatts. And the total power capacity of 20 wind projects, 20, is that all of them, right? These are 20 total, 20 largest wind projects, was 11,037 megawatts in 2013. The amount of energy produced in 1 hour at a rate of 1 megawatt is 1 megawatt hour. Okay, so they explain what a megawatt hour is. This sentence might confuse people. Again, megawatt is the rate that they're producing this energy. It's power, or unit of power. If you multiply that by the time, the hours, then that will give you the energy. Right, so that's what a megawatt hour is. The hour times a megawatt. If each of the 9 Texas wind projects, so the 9 was what I underlined in pink here, 9 wind projects, in 2013 had operated continuously for 24 hours, so it's the unit of time, at the maximum rate of power generation, approximately how many megawatt hours of energy would the 9 projects have produced? Okay, so just figure out how much energy. I guess we don't even need the stuff I underlined in red, the 20 projects you don't need. They're only talking about this Texas. And what is the table? 4,952 mega. That's the power capacity, I thought. And this is in, it adds up to 9. Oh, that's how many low, how many medium, how many high. They didn't talk about that at all in the word problem, though. Okay, so this is kind of interesting. You don't need this tape. Well, for one, I was going to say you don't need to use any of this other stuff in the table because we're only talking about Texas. But you don't even need this part. Like, it's just telling you basically where those 9 energy sources are as far as, like, are they low producers, medium producers, high producers? But they gave us the amount of energy from all 9, or the amount of power from all 9. Sorry, I should specify that's like how much it's producing per hour. So those 9 cumulative add up to 4,952 megawatts of power at their maximum capacity. So yeah, I don't think this table, I guess you could say it's kind of a red herring. Maybe they gave it because they're just like, oh, this is kind of interesting. You can look at it, but you don't use this table at all. I actually think if you try to use it, you'll probably mess up because there's no use of this 4, 2, and 3. The only thing I guess that is relevant is the 9, but you don't even use that 9 in your calculation. It's just knowing that that's the 9 Texas projects. So the only numbers you need are this 4,952. I guess the fact that the 2013s line up, right? It was like this data is from 2013 and they're asking about the 2013 projects, but you don't use that year in your calculation. And then the 24 hours. Okay, and like they said, the amount of energy produced, this is what I underlined in green, in 1 hour at a rate of 1 megawatt is 1 megawatt hour. So if we want to find how many megawatt hours, you just do the amount of, the rate of production in megawatts, that's 4952 megawatts, right, for those 9 Texas ones. And then you multiply that by the time, the number of hours, so times 24 hours, and that would give you, right, the number of megawatt hours of energy, right, the amount of energy that's produced in that 24-hour span. So if you multiply these two numbers, it gives us 118,848. Again, the units will be megawatt hours. It's megawatts times hours. And continuously for 24 hours. This doesn't say for a week, right? It's like just for 24 hours straight. Which does it say which is closest to that? Approximately how many? So this would be like a more exact number. I guess the closest to that is 120,000 of these options, right? You're just rounding to the nearest 10,000. Although the other options go to 1,000. I don't know. That's clearly the closest. It's much closer to 120,000 than 11,000. So D would be your answer there. Again, the main thing they're trying to trip you up with is this unit, the megawatt hour, and that it's kind of this massive red herring. They give you a table you don't need. They give you this data about the 20 projects, right? You only are focused on the 9 in Texas. But this one, like the actual math of it, it's like one-step arithmetic problem. You're just multiplying these two things. It would be hard to do in your head or on paper, but you can use your calculator. Just multiply the power, like the rate of power, and or you shouldn't say rate of power. It's just like you multiply the power of those 9 things total times the time. It gives you the energy. Okay, so that's how you do that one. Here we have if 4a over b equals 6.7 and a over bn equals 26.8, what is the value of n? Okay, well, we can quickly see how we can get like a over b alone here. So if they say 4a over b is equal to 6.7, then if you want to get the a over b alone, because you've got a over b here, you're just multiplying by 1 over n basically, then that would be divide by 4 on both sides. So divide this by 4, divide this by 4, just cancel, and it would give us a over b equals 6.7 divided by 4. And I'm just going to leave that as that for now. Okay, so that's a over b. Now, we know that a over b times 1 over n, right, you're going to say divide by n, is equal to this 26.8. It's equivalent to a over bn is a over b times 1 over n. So if we want to solve for n, we're trying to find the value of n. We just multiply both sides by n, and n divided by n cancels. Over here we get 26.8n. So it gives us that a over b is equal to 26.8 times n. Now a over b is equal to, we just solved this, 6.7 divided by 4. So let's write that here in place of the a over b, 6.7 over 4. And that doesn't mean a equals 6.7 and b equals 4. Right? It's just an equivalent fraction to a over b. And then that's equal to 26.8 times n. And now to get n alone, we'll just divide both sides by 26.8. So divide by 26.8, divide by 26.8. You think of that as like, essentially it's 6.7 divided by 4 times 26.8. I just wrote that in parentheses because if you type it in a calculator, that's how you have to do it. Otherwise, you'd have to write 6.7 divide by 4 and then subsequently divide by 26.8. But this cancels here. That would be equal to n. So if I type this in, 6.7 divide by 4, and then again, you could then do divided by 26.8. So like that. That would give you the correct answer. Or if you want to put it as, more similar to this format, then you need to use the parentheses. 6.7 divided by parentheses 4 times 26.8. Because if you don't use the parentheses, then it's just going to divide it will divide these two first, and then it will multiply by 26.8, which you don't want to do. You want to be ultimately dividing by 26.8 because it's in the denominator. So either of those will give you 0.0625, which should be the value of n, 0.0625. And is it multiple choice? It's not. So you could circle that as your answer. So 0.0625, or if you prefer to give it as a fraction, right, that would be, 625 over, we've got 1, 2, 3, 4 zeros, that's 10,000. 625 is 25 squared, or 5 to the 4th power. So, you can also use the math frac button on your calculator, or just ask it to return it as a fraction. But this would be 5 to the 4th over basically 10. It was supposed to be 10,000, I said, right? I said 10,000 and then I wrote 1,000. Should be 4 zeros, like I said, 1, 2, 3, 4. 10,000, that'd be 10 to the fourth, which 10 to the fourth, 10 is equal to 5 times 2, right? So 5 times 2 to the fourth in the denominator, and then you could distribute that fourth power. So it'd be 5 to the fourth times 2 to the fourth. Usually we'll say you can't distribute exponents because you can't distribute them to terms that are added, but you actually can distribute them to terms that are being multiplied. It'd be like that, the fourth. The power rule is like 5 to the first, 2 to the first. You're raising it all to the fourth, so multiply 1 times 4, 1 times 4, like that. But yeah, so 5 to the fourth will cancel. You're left with 1 on the top, 1 over 2 to the fourth, which we actually had 2 to the fourth in the previous problem. That's 16. So 1 over 16, which is equivalent to 0.0625. You can check that in your calculator as well. 1 over 16 is 0.0625. Okay, so either of those answers are acceptable on the SAT. You can put your answer as a decimal or as a fraction. The density of a certain type of wood is 353 kilograms per cubic meter. Okay, so density equals mass divided by volume. So they gave us the density, 353 kilograms per cubic meter, so per meter cubed. A sample of this type of wood is in the shape of a cube and has a mass of 345 kilograms. So they gave us the mass this time. And to the nearest hundredth of a meter, what is the length of one edge of this sample? Did they say it's a cube probably? Yeah, it's a cube, right? So that's a little bit, they made it a little bit more annoying. So you could just write over volume and then use that volume to then find the side length, the edge length of this cube. But I would be afraid that I would rush it. So once you find the volume, I would plug that in. And if it happened to be an answer choice, which it looks like it probably won't because these are all really close to each other, then I could throw you off. But what I will do, I mean, maybe it will be an answer choice, I don't know. But what I'll do is just write this as X, right? You could do it as S for side. The only thing is S's sometimes look like 5, depending on how you write 5. So just to avoid any confusion, I'm going to make it X. So this is X times X times X. Right, so it'd be X cubed is equal to the volume of this. So instead of dividing by the volume, I'm going to divide by X cubed, which is the volume of this shape. Right, so now if we want to get the X cubed alone, I'm going to multiply both sides by X cubed. And then I'm going to divide both sides by this 353 kilograms per meter cubed. So divide by 353 kilograms per meter cubed. Over here, divide by 353 kilograms per meter cubed. Okay, so we already have X cubed divided by X cubed cancels over here. 353 kilograms per meter cubed cancels out on the left side. And then over here, kilograms divided by kilograms cancels out. We end up with 345 divided by 353 times 1 over meter cubed, which actually means the meter cubes go up to the numerator. It's like basically this is meters to the -3 power in the denominator, so that flips up and becomes positive if you know your exponent rules. So that's equal to X cubed. We want to find X. So what we could do is divide, or not divide, we could take the cube root of both sides of these. Right? Cube root of the left side, cube root of the right side. Now cube root of meters cubed will just be meters. And I think, do they want it to the nearest hundredth of a meter? Right? You don't have to convert it into centimeters or anything. Hundredth of a meter is a centimeter, but we'll say this is X, right? Cube root of X cubed is X. And then meters cubed becomes meters. And now we just need to find the cube root of 345 over 353, which you could do the cube root of the top divided by cube root of the bottom. I think that's equivalent. Or, I'll just type it in like this. I'm going to actually write it like this in the calculator. 345 over 353 in parentheses. I'm going to put that to the 1/3 power. That's the same as doing the cube root. And so I'll do 3 parentheses, 345 divided by 353, close parentheses, to the 1/3 power. And it gave me X is about equal to 0.99238799066. I think it keeps going meters. And to the nearest hundredth of a meter, so hundredth be this place. 2 thousandths will round down, so this will stay as 0.99 meters, which is option B. If you want to check it, I guess you plug that back in and just be like, all right, well, 0.99287 or 79066. If you cube that, right, that would give you the volume. So cube it, gives you 0.977. Oh, so they were trying to trick you up there. If you found just the volume, it would be something that rounds to this. And then if you divide 345, so the mass by that volume, it gives you 353. Now you could do, if you don't feel comfortable doing all this stuff, is just cube all of these answers to find all the different possible volumes, and then just divide each of those, or use them as divisors. So divide the mass, 345 kilograms, by each of these cubed, right? Each of the volumes that would come from these side lengths, and then see which one is closest to 353. And, you know, since this is a rounded value, none of them will be exactly 353, but you'd find that the 0.991 will be the closest. All right, a certain town has an area of 4.36 square miles. Okay, so 4.36 miles squared. I always write miles as MI, so I don't get confused with meters. What is the area in square yards of this town? Okay, so we're just converting miles squared into yards squared. Just make sure you have to basically convert it 2 times. If it helps you, you can think of this as miles times miles, right? So you have to convert these miles to yards and these miles to yards. I'm just going to leave it as miles squared. Okay, if it helps you to do that, that's fine. So in this case, I mean, I did say if you want to get something out of the numerator, you would put it in the denominator. If there's no fraction, just think of like everything is the numerator then, right? There is no numerator or denominator. This is like this over 1. Okay, so we're multiplying it by something with miles in the denominator. And we know 1 mile is 1760 yards. They gave us that, luckily. It's interesting. With the imperial system, I think most people would not know that number off the top of their head. I don't think I would. I would know the feet in a yard, or feet in a mile, and then since you know feet in a yard, you just multiply that by 3, or divide that by 3, yeah. Because there are 50 to 80 feet in a mile, so divide by 3 should be 1760. But yeah, I mean, this is just not a number we use very often. But I would have known the meters in a mile just from, right, if you run on a track, you have to do the 1600 meters plus an additional 9 to approximately cover a mile. But anyway, so this we get rid of one of those miles. We want to get rid of miles squared, so we have to multiply by the same fraction twice. 1760 yards over 1 mile. Again, we can multiply by this because this is equivalent to 1, right? It doesn't change the value because 1760 yards is equal to 1 mile. So if you divide it by itself, it doesn't change the value. And then we get, right, miles squared divided by miles, just miles. And then miles divided by miles is nothing, or it's just 1. And then we're left with yards times yards. Right? So we will end up with 4.36 times 1760 times 1760. We're going to write times 1760 squared. Yards times yards is yards squared. I'm just going to type this in my calculator. 4.36 times 1760 squared. I'm just squaring the 1760 part. Again, you could type times 1760 times 1760, will be the same thing. And that gives 135,05536. Should we put these in? That's 13,505,536 square yards. Again, we wanted our answer in square yards. That's good. And, oh, I thought they were going to round it, but it is D, exactly. Perfect. To study the moisture content in a group of trees, samples from the trunk of each tree were taken from 25 trees and cut in the shape of a cube. Okay, so we've got a cube. They really are liking cubes in this set. So we've got a cube that is a sample of tree trunk, right? Or a sample from the trunk. The length of the edge of one of these cubes is 2.00 centimeters. So if it's cubed, then the length, width, and height are all the same. They're all 2.00 centimeters. I'm just going to write centimeters on one of them so I keep track of that. Could just write that as 2, but you know, whatever. If we're keeping track of sig figs, which don't matter for the SAT, they won't expect you to do sig figs, but I'll just do it for the academic exercise here. I'll make sure that looks more like a 0, not a 6. If this cube has a mass of 2.56 grams, so the mass equals 2.56 grams, what is the density? Here's another density question. So density is going to be equal to the mass divided by the volume. So this time they gave us the mass and the volume. We just have to calculate, or they didn't give us the volume per se, but they gave us a way to find the volume. So this one would say the density is equal to that mass, which is 2.56 grams. And they want it in grams per cubic centimeter. Nice, that's the units they gave us, grams and centimeters. We don't have to convert to meters or anything. And the volume we could find, the volume is going to be equal to that side cubed, or you just do 2.00 centimeters times 2.00 centimeters times 2.00 centimeters. Right? But for a cube, you can just cube that side. So I'm going to cube 2.00 centimeters. 2 cubed is 8, so 8.00 centimeters cubed is our volume. So 2.56 grams divided by 8.00 cubic centimeters, like that. And I think that's just going to be the answer. That's the units they want. I mean, you have to type it in your calculator, but just type in the numbers there. So 2.56 divided by 8. I mean, you write 8.00, the same thing. And now if we were doing proper sig figs, we should go to 3 sig figs. So it should be like 0.320. The calculator just says 0.32. Sig figs do not matter on the SAT. I should just not even talk about this. Now, if you were in chemistry class, you'd say this, grams per centimeter cubed. But in this test, just say that, grams per centimeter cubed. You do not need to give the units. You shouldn't. There's nowhere to even put the units. So they'd say how many grams per cubic centimeter is 0.32. Okay, so that's your answer. I guess you could do it as a fraction. This one seems like it lends itself more to doing it as a decimal. If you wrote it as a fraction, you'd start with 32 over 100. It's 32 hundredths. And then both of those are multiples of 4. So you could divide the top by 4, gives you 8. The bottom by 4, 100 divided by 4 is 25. So 8 25ths should be the same thing, 0.32. And that's fine, I guess. Just if you have a fraction, make sure it is fully reduced. I would write this 0.32 or 0.32, but they should accept the fraction as well. All right, to study fluctuations in composition, samples of pumice were taken from 29 locations. So pumice is that rock that has like all the holes in it it was like basically gas bubbles while it was cooling. So it's kind of got like a spongy texture. Not really spongy, I guess, because spongy means makes it sound like it's softer than it is. But it's just a bunch of holes in it. It's kind of interesting. And I don't think that will matter, though. Taken from 29 locations and cut in the shape of a cube. The length of the edge of one of these cubes is 3.00 centimeters. It's going to be another density question. It's sounding like it. So 3.00 centimeters for the edge of the cube. That's 3. This is centimeters. This cube has a density of, they gave us the density this time. So the density, again, which is equal to the mass divided by the volume. The density is 0.230 grams per cubic centimeter cubed. What is the mass? Okay, so they want to find the mass. I think finding the mass is probably the easiest of these because you don't have to do as many steps. It won't be as much algebra. So they give us the volume. I mean, volume is going to be equal to the side cubed. So 3.00 centimeters cubed. You could also multiply length times width times height, but that would be the same thing. 3 cubed is 27, so it's 27 technically if you're doing sig figs, 27.0 cubic centimeters. I don't know why I keep saying sig figs, they don't matter on the SAT, but it's an important concept in chemistry. So we'll divide that by 27.0 centimeters cubed. And now to get the mass alone, we just multiply both sides by that 27.0 centimeters cubed. Like that. And it'll cancel out over here. Centimeters cubed divided by centimeters cubed cancels 27.0 divided by 27.0. We're left with just the mass on this side. Mass is equal to, now we can multiply these numbers, 27.0 times 0.230 is 6.21. So 6.21 centimeters cubed divided by centimeters cubed cancels. We're just with 6.21 grams. What is the mass of the cube in grams? They don't say how to round it. So I would just give the exact value here, 6.21. This one, I would be very mad if someone gave this answer as a fraction. Like if it was my test. I think they technically have to accept it as a fraction. Please just write it as 6.21. Or unless maybe your calculator is returning it as a fraction, but that'd be kind of silly. Objects R and S each travel at a constant speed. Okay, R and S, let's do maybe 2 different colors for them. Travel at constant speed. The speed of object R is half the speed of object S. Okay, so R is slower, but we could say like the velocity of R is equal to half the velocity of S, right? It is half the speed. So half of velocity S. Which again, velocity S being bigger means it's moving faster. So it will take less time to do things, right? Sometimes people will mess up velocity time because velocity and time have kind of an inverse relationship. The faster you go, the less time something will take, and vice versa. If you take longer, that means you're going slower. Object R travels a distance of 4x inches. So R travels 4x inches in y seconds. So that is the velocity, like distance divided by time. Which expression represents the time? And let me just underline those so you can see where they came from. Which expression represents the time in seconds it takes object S to travel a distance of 24x inches? So 24x inches. It will not be equal. I can't set up an equation here because, again, this one's faster. Now, VR equals 1/2 of VS. Oh, wait. Yeah. So what I could do is say it's equal to 1/2 times this velocity S, which, again, they only give us the distance. They only give us what would be in the numerator, 24x, over, we don't know what goes here. Right? This is the time. Right? That is t. Okay, so you could set up an equation like this. That's one way to do it, and then you just would solve for t in terms of y. I'll show you how to do that just quickly. So 24 divided by 2 will give us 12. So 12 there, and then divide both sides, or let's get the t in the numerator. So multiply both sides by t, cancels out here. We get t, and then to get rid of this times 4x over y, you'd multiply that by the reciprocal, so times y over 4x on both sides. So times y over 4x. The x's will cancel out. 12 divided by 4 is 3. So you're left, I know this is like kind of messy, but the only things that are not crossed out are 1 times 3 times y, 1 times something doesn't change the value. So you just have 3y over here, y divided by y cancels, 4x divided by 4x cancels. So t equals 3y. Right, so you could do it like that. Now, if you want to actually maybe think about it a little bit more conceptually, you could say, we know that the slower one, VR, goes 4x in y seconds. So how long would this one take to go 24x inches? You'd multiply it by 6 over 6, right? Multiplying by something equivalent to 1, so it's not changing the actual value. But this would be 24x over 6y. So at the same rate, 4x over y, because it would travel at a constant rate, it would go 24x inches in 6y seconds. So that's how long it would take this one to go 24x inches, 6y seconds. But this one is half as fast as the other one. So again, like we said, if it's going faster, it will take less time. If we want to figure out like how long this one takes, you have to divide it by 2, like the time. So basically, you could write it as an equation again if you want. 24 over 6y equals 1/2 times 24x over this time. And then you would just think, all right, well, what would make this true? Right? They both have 24x in the numerator already. What would make 2 times t equal to 6y? Well, t would have to be 3y. Or you can just say it takes half as long because it's going twice as fast. So it's going to be half of 6y is 3y. So no matter what you do, you're going to arrive at 3y as your answer. Just whichever way helps you conceptualize that. Just make sure you know that velocity, or they say it as speed, I think, right? Speed is equal to distance divided by time. For an electric field passing through a flat surface perpendicular to it, the electric flux, so the electric flux of the electric field through the surface is, electric flux is going to be equal to, is what they're saying, I think. Electric flux. And this previous stuff is just like the conditions that you need for this equation to work. So it has to be an electric field passing through a flat surface that's perpendicular to the field. So it's like some surface like that, and for it to pass through it, right, like that. All right, so that doesn't actually matter. It just means like that needs to be true for this equation to be true. Electric flux will be equal to the product of the electric field's strength. So electric field strength, product means you're multiplying, so times, I don't know if it's dot product or cross product, but times the area of the surface. So times the area of the surface. Interesting, they didn't say surface area, but I guess because it's a flat object. So, I mean, you're not doing like the top and bottom of this flat thing. I guess, that makes sense. A certain flat surface consists of 2 adjacent squares where the side length in meters of the large square is 3 times the side length in meters of the smaller square. So the side length is 3 times, which actually means the area is going to be 9 times. Right? If we draw it out, right, like I didn't say what the numbers are, but it could be, say this one's x and x, then the other one will be triple that, so it'd be 3x and 3x. And I didn't draw that to scale, but right. So they're both squares. One's 3 times the length of the side. Okay, they're adjacent, so they're touching like that. An electric field with strength 29 volts. So this is the field strength. So this red thing here is 29. Do it red. 29 volts per meter. I don't think you need to really understand where the units are coming from. Just make sure you keep track of them. 29.00 volts per meter. Yep. Passes uniformly through the surface, which is perpendicular. So this is just, it's meeting the requirements. It has to be perpendicular to the surface, the electric field, and it passed uniformly through it. Okay, so we can use the equation, essentially. They gave us this information. If the total electric flux of the electric field through the surface is 4,640 volts, oh, volts meters. I feel like that should be volts meters. I don't know. I haven't taken E and M in a while, and I was a little bit checked out because it was second semester senior year of high school. But anyway, we've got 4,640 volts meters is the total flux. So that's the pink thing here, electric flux. And they say total, so that means of like the stuff going through like both of these. I'm not fully conceptualizing flux here, but whatever, that's equal to 4,640 volts meters. So volts times meters is equal to this 29.00 volts per meter times the area of the surface. Does that make sense? Because area of the surface will be in meters squared. If you multiply volts per meter times meters squared, it'll get rid of this, the meters in the denominator, and multiply by an additional meters, which give you volts meters. Okay, that makes sense. What is the electric flux in volts meters of the electric field through the large square? Okay, I thought they were gonna ask for the area of the surface of one of them or something, but let's see. What is the electric flux of the electric field through the larger square? What they gave us was the total. Okay, so they didn't give us just one of them. They gave the total that's going through both of them, and we want to find just what's going through the larger square. I think that'll just be proportional to the size, right? So like we said, the area of this one is like it's x squared, whatever x is, and this one will be 9 times that, so 9x squared. So if we're just multiplying it by the area, I mean, you multiply the total area, you're multiplying by x squared plus 9x squared. You're multiplying each of those by 29 and then adding them up. But if you're doing just the big one, you're just doing this 9x squared. So combined, this makes, right, it would be like 4640 volt meters is equal to 29.00 volts per meter times x squared plus 9x squared. And again, they don't use x squared or x anywhere in this. I just assign that for the length of the sides. I thought they're going to ask that. That'd be 10x squared. All right, so you're ultimately multiplying this by 10 times the area of the small one. Now, if we only want to do the big one, then what we'd be multiplying it by is 29.00 volts per meter times 9x squared, right? Because we would only be using the big square, right? This one. So you see the only difference between this and this is you're multiplying basically by 9/10. Right? It's 9 of the 10 total units of area. We don't even need to know what that x squared is to know that that's the case. So if the multiplying it by 10x squared gave us this, then to find what multiplying it by 9x squared is, you could just multiply it by 9/10. So you could say 4640 times 9 over 10, and I mean divided by 10 will just be 464. So we do 464 divided by, or 464 times 9, and that would be 4176. Again, it's volt meters or volts meters, I think they said. It's the electric flux. So that should be your answer. We could say 4176. Now, I mean, a lot of times the ones that are like hard to conceptualize what the problem is or how to set up, or that you'd be confused, because I would not have known how to set up an electric flux problem from the top of my head. I just used the information they gave here. So don't be intimidated like, oh, I don't understand any of this stuff. The electric field strength, air. I hardly understand it. I know maybe it sounds like the way I just explained that, it sounds like I know what I'm talking about, but I just went part by part, said, okay, they gave us this as like a condition. That condition is met. Then they said the electric flux is the product. So this is, when you say is, usually it means equals in a math problem. So the electric flux equals the product of this times this. So I just wrote that out. Electric flux equals this times this. You don't need to know what any of those things are. Then they gave you this. The only, I think, tricky part is this stuff with the areas here. So like that this area is 3 times this, or this part of the square is have a side length that's 3 times the smaller one. So just draw it out like that. And then I think the key word here is that it's the total electric flux is what they gave you. So the total is this number, 4640. And that means you're multiplying this electric field strength, the value they gave you here, volts per meter, says the electric field with strength, it's the strength, and then you're multiplying that by the area of the surface, which is, they said total, so it's going to be the area of this and the area of this. And then ultimately, we want to find the electric flux when you're just using this area. Another, you know what, I'll show how to do it, like how to find the area of that maybe. So just working, I guess using this thing here, we could find what x squared is by dividing by 29 and then divided by 10. Or I could think of it as divided by 290. So we're getting it so it's just the x squared alone. So you'd have 4640 volt times meter divided by 29.00 volts divided by meters, and then also dividing by 10. And then we're just left with x squared over here, which is the area of the little one, right? The little one, not the big one. So that would give 4640 divided by, I'm just write divided by 290. That's divided by 29 and then divided by 10. That gives us x squared equals 10. Oh, okay. It's a nice even number. It's a perfect square. So it's 16. And let me put the units as well. So let's see. Volts cancels out. And then if you divide by 1 over meter, it's actually like multiplying it by meter. I think of divide by a fraction, you multiply by the reciprocal. Or you can think of this as it's like meters to the -1 in the denominator. So you flip it up to the top, make it, multiplying by meters to the first. So this would be 16 meters squared equals x squared. That makes sense because it's an area. So that means that x, the side length, would be the square root of that, so 4 meters. So if x is 4 meters, then if we want to find the area of the big one, we would have to go, okay, well, that means that 3 times it, right? Because the sides are 3 times that. So 3 times 4 meters is going to be 12 meters. And then when you square that, right, it gives you 9x squared is equal to 144 meters squared. So now we could plug this number in as the area for what we're trying to solve, which is right, basically 29 times 9x squared. This is 9x squared. So you do 29.00 times 144, and that gives you 4176. Right? So 29 times 144, that would give you volts per meter times meters squared. So that ends up with is equal to 4176 volt meters, right? Because the meter squared cancels with the meter on the bottom, and then you get meters up top, right? Like that. So 4176 volt meters is the same thing we got by multiplying the original value they gave us, the 4640, by 9/10. So either of those ways will work. They'll give you that same thing, 4176. Now, this was a tricky problem, not because of the math. Like the actual math involved in it, not that difficult. It's more like the physics of it. So how to set up the problem, how to understand what's going on. And then I think the trickiest part to understand, as long as you're reading carefully, the hardest part would be like figuring out what you're doing with these areas and make sure that you understand that. Because I still am not really getting how this works, like what electric flux is, or why you can just use these 2 adjacent areas and add them up or whatever. But whatever, they kind of explained in the problem how you plug it in and what the stipulations need to be. It seems to meet those stipulations, so I believe this would be how you would do it. All right, here we have a landscaper uses a hose that puts 88x ounces of water in a bucket in 5y minutes. Okay, so if we do like amount of water per minute, it's 88x divided by 5y. And it doesn't say anything about like hose A and hose B or something like that. But so we've just got this one hose does 88x ounces of water, maybe I'll write ounces, in this many minutes. So ounces per minute. So this gives you that rate. Which expression represents the number of ounces of water that the hose puts in the bucket in 9y minutes at this rate? So basically this is equal to some amount of water. I'm going to call that, can't use x or y. Let's call that W for water. So how much water in, they gave us 9y minutes. So at the same rate. So we just set up a proportion. And we could think of it, and this is also minutes. Basically, we know our answer is going to end up in ounces, because you multiply both sides by minutes, you get ounces left. We're just solving for W, so we could just multiply both sides by 9y. Some of my kids would cross multiply or do like, some kids call this like the butterfly method. You could do that, but then you end up having to divide by 5y anyway. So I'm just going to multiply by 9y, get that W alone. And we get that W is equal to, well, over here, we've got Y divided by Y will cancel out. So we have 9 times 88x over 5. And we're going to be left with an x, but it looks like, yeah, all the answer choices do have x's in them, so that's good. So we just type this in. Oh, we can't type the entire thing in because they want it as a fraction. Right? They want this. Now, neither 9 nor 88 has 5 as a factor, so it looks like the 5 is going to stay, which actually knowing that, it's probably going to be D. But let's do 9 times 88 gives us 792. That's 792x in the numerator. And we're still going to have that 5 in the denominator. That's equal to W. All right, so we know that that would be 792x over 5. As I said, it's the only one with 5 in the denominator, but make sure you do it fully all the way through. That is the numerator. When the denominator is 9y, you set up a proportional fraction. The area of a rectangular region is increasing at a rate of 250 square feet per hour. Which of the following is closest to this rate in square meters per minute? So there's another unit conversion one. I guess that makes sense because it's units is one of the things on here. But we've got 250, what is it, square feet, so feet squared per hour. Which of the following is closest to this in square meters? So I'm going to change feet squared into meter squared per minute. And we change the hours into minutes. I'm going to start with the minutes. We know there are 60 minutes in 1 hour. And we have hours in the denominator, so we want to get minutes in the denominator. Multiply by something with minutes in the denominator. We're going to multiply by something with hours in the numerator, so it cancels out the denominator hours. So we said 1 hour is equal to 60 minutes. You don't need to write that one. It might help you to make sure that you actually put the unit in, but whatever. I'll just put it in, I guess. We're doing 1 hour over 60 minutes. That's equivalent to 1, right? Those two things are equal to each other, so it's divided by itself. It's equal to 1. It doesn't change the value. It's just changing our units. As we said, the hours will cancel out, so we'll be left with minutes in the denominator. And now we need to change, what is it, square feet into square meters. They gave us this one. So 1 meter, and we want to get meters in the numerator, so let's write 1 meter in the numerator. We want to get rid of feet in the numerator, so we put feet in the denominator, is equal to 3.28 feet. And that will get rid of, like, one of these feet. It's feet times feet. We have to multiply by the same thing twice, or you can do the same thing squared, you could say. So we get rid of both of these, right? Feet squared divided by feet is just feet, and then feet divided by feet is 1, and then we're left with meters times meters, meter squared. All right, so ultimately we'll have 250 times 1 times 1 times 1, and the units will be meters times meters, which is meter squared in the numerator. And then in the denominator, the hours already canceled out here, so we have 60 times 3.28 times 3.28, or you could write that as 60 times 3.28 squared, and it is minutes, and all the other units are canceled out, so minutes in the denominator. All right, and that's what we wanted, square meters, so meter squared per minute, so that's good. So we just need to type in these numbers, 250 divided by, now you could do parentheses, 60 times 3.28 squared. Again, you're just squaring the 3.28 part, right? But I put that whole thing in parentheses so that you're dividing by all of that, right? That will work, gives you this 0.387, I'll write the rest of it in a second. Or you could also write it as 250 divided by 60 divided by 3.28 squared. Now, I don't need to put parentheses around the 3.28 before I square it, because this will know order of operations exponent squared comes before division. But I can't do 60 times 3.28 squared, because then it will do this division first, and then subsequently multiply it by 3.28 squared. We don't want to multiply by 3.28 squared. It's in our denominator, so we want to divide by that. So, but either of these ways, if you divide and then divide, or you can even do 250 divided by 60 divided by 3.28, and then divide by 3.28 again, they'll all give you the same answer, which is 0.38729422693. This is an approximation. What is that? Meters squared per minute. And did they say what's it rounded to? Which is the one is closest. So just closest to this. All right, well, the only one that's even less than 1 is A. That's 0.39 is this number rounded to the nearest hundredth. It's 0.39 meters squared per minute. Right, that makes sense. Anita created a batch of green paint by mixing 2 ounces of blue paint. So it's 2 ounces of, 2 ounces of blue paint with 3 ounces of yellow paint. So the proportion, it's 2 ounces to 3 ounces, blue to yellow. And I'm doing yellow and orange, I know, but whatever. That's what I had available there, and I think orange shows up a little bit better in here. Now, if you do mix blue and orange, it would probably make brown, whereas blue and yellow would make like more of a green, but whatever. It doesn't matter for this problem. She must mix a second batch using the same ratio, this 2:3 ratio of blue to yellow paint as the first batch. If she uses 5 ounces of blue paint, so 5 ounces of blue, then what is he going to say? How much yellow does she need? 5 ounces of blue paint in the second batch. How much yellow paint should Anita use? Okay, well, the answer choice is a little weird here, but we'll just figure out the number first. So a couple ways you could do it. You could do like, what do you have to multiply 2 by to get 5, and then multiply 3 by that same thing, which would be, I guess, 2.5, right? So it'd be times 2.5, and this is also times 2.5, like that. 3 times 2.5, 3 times 2 is 6, times 0.5 is 1.5, so that would give us 7.5 ounces. You could do it that way, or you could say, all right, the ratio of these two stays the same, so, right, like 2 over 3 is going to be equal to 5 over, I know we now know it's 7.5, but say x, like that, then just cross multiply this all for x. You'd say like 2x equals 5 times 3 is 15, divide both sides by 2, x equals 7.5. So you can do it that way. I guess you could think like, what do you have to multiply 2 by to get 3? You have to multiply 5 by the same thing. But okay, let's see what they have. So exactly 5 ounces? No, we want 7.5 ounces. It's definitely not that. 3 ounces more than the amount of yellow paint used in the first batch. No, they're saying, okay, so you added 3 to 2 to get 5, so you have to add 3 to this. No, that would be like, you're not keeping the same proportion. You would have the proportion you had, and then you would be combining it with one that's like equally mixed between the two. That's not what you want. You want to combine it with like the same ratio. So you could add like 2 to 1 and add 3 to the other, keep the same proportion, but then you wouldn't have 5 ounces. 1.5 times the amount of yellow paint used in the first batch. No, that would be 2.5, right? 2.5 times, right? If you're going to multiply this by 2.5, you have to also multiply this by 2.5. Not 1.5. That would be if it went from 2 to 3, but it went from 2 to 5. So it's not that, which means it's going to be D, but let's see, also 1.5 times the amount of blue paint used in the second batch. Oh, in the second batch. So this was first batch, this is first batch. In this batch, so 1.5 times 5, which is 3/2. Okay, the 3/2 is equal to 1.5. So that ratio of yellow to blue is 3 to 2, which is equal to 1.5. So if you have your blue amount, you multiply it by either 3/2 or 1.5, you get your yellow amount. 5 times 1.5 is 7.5. Okay, so that checks out. I guess they thought it was too easy if they just put it as 7.5 ounces as an option, or 2.5 times 3 ounces. But yeah, I mean, there's another way to think of it. I think I even said you could do that. I just was too lazy to actually do the math with it. But okay, so D, 1.5 times the amount of blue paint used in the second batch, so in that same batch. All right, the density of a certain solid substance is 813 kilograms per cubic meter. So we know density is equal to mass divided by volume. The density, they gave us 813 kilograms per cubic meter, so meter cubed. A sample of this substance is in the shape of a cube, where each edge has a length of 0.6 meters. Okay, so we draw our cube, and it's 0.60 meters. I'm writing the units for all of them this time, I guess, I don't know. To the nearest whole number, what is the mass? Okay, I like the ones with math where they ask for the mass, because I think those are the fewest steps to do. Maybe that's making me seem lazy, but for this one, we want to find the volume. They gave us the sides, so we could just do parentheses 0.60 meters and parentheses cubed. You just multiply in length times width times height. They're all the same. And that would give us, right, you can think of it as 6/10 cubed. So the 10 cubed would become 1,000. 6 cubed is 216. So it's going to be 0.216 meters cubed is meters cubed. So 216 over 1,000, like that. So that's our volume. You can also do that in your calculator. Don't feel like, oh, do I have to know all these cubes in my head? No. Just, I guess, a combination. I have a coached math count, so I know a lot of these cubes off the top of my head, and maybe I'm a little bit too lazy to pick up my calculator and type it in. But we've got this, and we just need to get the meters alone, or not meters alone, the mass alone. That's why I did it as a different m. I still mess it up. So multiply both sides by this denominator, 0.216 meters cubed. 0.216 meters cubed. And here the meters cubed will cancel out. And here the meters cubed will cancel out. Meters cubed divided by meters cubed. So we're just left with kilograms on this side. 0.216 divided by 0.216 is 1. So we get that the mass is equal to 0.216 times 813 kilograms. 0.216 times 813 gives us 175.608 kilograms. And they say to the nearest whole number. So 0.6 will round up. That will give us 176, which is choice A. Right, if you want to check it, just do 176 divided by the volume that we had. So I'm going to write 176 divided by 0.6 divided by 0.6 divided by 0.6. It does give me 814.814. That's very close to 813. If you did the same thing with the other ones, it would be much further off. So that would be that one. And here we have a certain park has an area, it's a huge area. Well, it looks huge, just in square yards, of 11,863,808. I guess you don't really need the commas to do the math, but just make sure I didn't miss anything. Yards squared, square yards. What is the area in square miles? We're just converting from yards squared to miles squared, and they give us the conversion rate. So again, yeah, even though we'd already had a problem with that, I don't think I would have remembered that number. I would have had to do 5280 divided by 3. But they should give any like obscure unit conversions, they'll probably give you. It seems like they're not giving 60 seconds to a minute or 60 minutes to an hour. Just, hopefully you know those. I'm trying to think what else they have not given. I think they give anything else. So even if they did centimeters to meters, they might give you 100 centimeters to a meter. Like I don't think they expect you to know the metric prefixes or even conversions between imperial units, so inches, feet in a yard, things like that. But for this one, they gave us 1 mile equals 1760 yards. Again, we don't really have like a numerator or denominator, but you could think of this as being all over 1 if that helps you. Otherwise, just think of it as the numerator. And we want to get rid of yards squared. So we're going to do something that we're dividing by yards 2 different times. Times something over yards and something over yards. And we want miles squared, so we want to multiply by miles twice. So 1 mile in the numerator for both things we're multiplying it by. And the yards should be what's equivalent to 1 mile. So we're not changing the value. If you multiply by something divided by itself or divided by an equivalent value, it doesn't change the value. We'll just change our units here. If we multiply by 1 mile over 1760 yards 2 different times, right? Or you could think of it as multiplying it by 1 mile over 1760 yards, all of that squared. Then we'll go, let's say yards squared divided by yards is just yards. And then yards divided by yards is 1. So we got rid of those units. And then we are left with miles times miles is miles squared. So we have this number, 11,863,808 divided by 1760 squared, or divided by 1760 divided by 1760. So I would do 11,863,808 divided by 1760 squared. You don't need to put parentheses if you're squaring it, because again, order of operations squared would come before division. You could do it if you feel safer about it, but it gives you 3.83. So that would be 3.83, and then again we have miles times miles is miles squared. Just always check what do they want the units in, square miles, so we did it correctly. Assume we did. That would be option B. And that's the last one. All right, so we are done with what are these? The ratios, rates, proportional relationships, and units hard difficulty questions. I decided to skip doing the easy and medium just for now. I know some people are taking the SAT this upcoming weekend, so I'm trying to rush as many of the hard videos as I can. I think those are the ones that seem to be getting the best response in terms of these are the most helpful ones. Because, I think if someone is taking the time to prepare for these, probably the hard ones are where you want to spend the bulk of your preparation time, especially as you get closer to the test. I think the easy and medium ones can be valuable early on. Make sure you fill in any gaps and to get your speed up. But I'm going to try to prioritize getting as many hard ones out as I can over this next week. And then maybe I'll try to get mostly hard ones done first and then move on from there to fill in all of the easy and medium ones. They did recently add a few new questions in each category. So for instance, I had made a PDF with all of the questions of this set, and I think there were 16. And now in this set, there were 17 when I checked a couple of days ago. So I will probably have to go back and add in a couple of explanations for some geometry and algebra sets that I've already done. But I'll prioritize probably getting the ones that I have not done any of them yet as soon as I can. And just, going over these quickly, there were a lot of these ones that were unit conversion. Some of them just had 1 unit, but it's squared. You have to make sure I do the unit conversion for the square units, not just for the units. Some of them had multiple different units in it. So just make sure you set it up like this. I mean, you don't have to set it up like this to solve it. I've had a lot of students who just say, why can't I just divide? I know what I have to divide. I know what I have to multiply. Those same students will often make at least one mistake on a test or something. And I say, if you do it this way, you're not going to make mistakes. As long as you take your time, do it thoroughly, match up your units, make sure. But if you want to get rid of a unit that's in the numerator, or just, if there's no fraction, then it's equivalent to being in the numerator, then you need to put that same unit in the denominator, right, to cancel it out. Whatever you want to be in the numerator should be in your numerator, what you multiplied by. Vice versa for the denominator. I don't know if you'd say vice versa in that case, but the same thing for the denominator. If you want to get something out of the denominator, multiply by that unit in the numerator, and whatever you want in the denominator, multiply by something with that in the denominator. All right, so just do practice with these unit analysis ones. There are a lot of these on Delta Math, so you could even make a set for yourself or ask someone to make them for you. You could look for some practice ones. They feel tedious at first, but I actually found them kind of fun, like they're little puzzles. You can find ones that have tons and tons of units. That's what the Delta Math has, really hard ones that have like 7 different units involved, and you just have to keep track of all this stuff and multiply and divide correctly. They'll give you all the conversion rates. And as long as you have a calculator and you don't have to do all this math by hand, then it's kind of fun. You cross out the units. It's, again, like a puzzle. So you end up with the units that you want. Density of certain things. Okay, so there were a lot of density questions where they either give you the density and the volume, you have to find the mass, or they give you the mass and the volume, you need the density, give you the mass and the density, you need the volume. It seems like mostly for the volume ones, they're not actually giving you the volume, they're giving you the dimensions. I think the hardest one was when you had to find the dimension. Just harder because you had to add in that cube root step of it. It's not really that difficult, but just it is an additional step and something you have to remember to do. And I think to make it trickier, they did make just the volume one of the answer choices. So be careful of that. This one is just a proportion question. It was a little bit odd how they asked it with the answer choices, but as long as you understood that one, it should be good. Another unit conversion. They had a couple like this where there were ratios that they gave you. It's just like the rate of doing something or the rate of moving, but they had variables in it. So just make sure you're comfortable with having an answer that still has variables in it. I think they would call this a literal equation, or it's similar to literal equation problems if you did that in algebra. Just make sure you're comfortable with that. This one was weird. So make sure that you maybe rewatch this one. If you still don't get it, comment that below and I'll maybe make a better explanation or a more thorough explanation. I think I went through it pretty thoroughly. I spent a lot of time going through, like the actual math of it, you could do very quickly. Like once you know that you're just multiplying this by 9/10, or even if you want to do it the other way, like this didn't take that long, but it's more just setting it up, making sure I'm keeping track of all the variables. And then I spent a lot of time explaining it. So hopefully on the real thing, you're not going to take that long to do it. But, just have the attitude, I don't need to understand what this equation exactly means or how I could use this in the real world. And if you're taking physics class, it'd be valuable to know like when it's useful or when you would use it. But for this problem, right, they gave you how to set up the equation. They gave you some of these variables. You just had to make sure that you knew what to put where. Read closely. It's just as much a reading comprehension question as it is a math question, right? So just take your time on this kind of problem. Here's the one, another one, they had the kind of like literal equations. You're solving for something in terms of a variable. Be careful with velocity and time. Just they do have that opposite relationship where if velocity goes up, the time it takes goes down. If the time it takes goes up, the velocity is going down, right? That means you're moving slower to do something, take longer to do something. Here's another density question. They had a lot of those. Unit conversion. What is this? This is a density one. This is the density one where we had to find the actual length, so it made it a little bit more difficult. And this one, it's kind of like the literal equations. This one was probably the easier of those literal equation ones. I just found it in terms of A or B. Just make sure you're comfortable like moving variables around, having values that have multiple variables in them, but you're just solving for one specific part of it using multiple equations. This one was not that hard. It's another one where like they're having a physics concept that I think they're hoping will scare some people. Like, oh, I don't know how to do this. You don't need to know how to do it because they give you all the information you need. They also gave a lot of information you don't need. So I would say this question was the biggest red herring. They gave you this whole table that was just useless, and they gave you some other information about the 20 largest projects. I mean, it's interesting. I'm not saying it's useless in all facets of life, but for this question, a lot of this stuff you did not need, which is whatever. That's how they chose to do it, to make it a little bit more challenging. That's why it's in the hard section. This one kind of didn't fit with some of the other ones. I feel like more to do, not exponential. I mean, you could say it's like 2 to the x power. It's also interesting they had like the money doubling. Like usually if they're doing money, they'll do a more reasonable like rate of return. But I don't know, investment account doesn't say what he invested in. So I mean, there might be some things that are really high growth early on. And it was just going from $30 to $480 over 4 years. But This one I would probably, I'd probably recommend just do it the easy way, where you're just kind of like going backwards or doubling. Not that this is very difficult, but maybe make sure you're comfortable doing both. But don't be afraid to do something. Like if it's only a span of 4 years, you can just write out all the numbers and figure it out. It'd only be tough if they're like over this 15-year span or this 200-year span. 200, you would not be able to write them all out. 15 it'd be tedious to do it. Then that's when you'd want to use a method like this, because you could use your calculator, do it a lot faster. And what is this? Another rate, unit conversion. This is density or unit conversion? Density. And then this was the first one, I think. Yeah, the first one. This one was just annoying because they used that word growth factor. And in your head, like if you've done any questions with growth factors before, you'll know having a high growth factor means it grows fast. Having a low growth factor means it grows slowly. But it was the opposite here because it's not really a growth factor. So just read that carefully. I think conceptually this one might be tough. The actual math involved, not that tough, right? It was just 1/5 times 10, 1/3 times 10, but just you'd have to figure out where that 1/5 and 1/3 came from with a decent conceptual understanding. And again, you could call this a red herring. It's more just knowing that, right, here's a table. You have to be able to find the things on the table that you need to use, and they reference them. At least this table is not nonsense. Like you did need the table to answer these questions, but like you'd say, oh, like a lot of this I didn't need. And again, that name growth factor, I'd say it's a little bit of a misnomer. All right, but so that's all of those questions. If you have any questions, concerns, corrections, anything that you have about one of those questions, even if you want me to like re-explain one of them, maybe I can make a short for it, comment that below. Really appreciate any of those feedback. If there's something that you found especially useful, or like maybe, oh, don't waste your time with this, do this, comment that back below as well. If you found this video useful, make sure you like and subscribe if you haven't already. That will just promote more videos like it in your feed. And if you're taking the SAT very soon, good luck. Thank you for spending your time watching my video, and hopefully it was helpful.